So I want to tell you today the story of the search for exoplanets in the Alpha Centauri system. And this search for exoplanets has kind of intensified over the last few years. And there have been already some announcements of planets that have been detected. And I will talk about all of this. And of course, the Alpha Centauri system is kind of special for us because it's our next door neighbor. So let me introduce you first to our neighbors. There are 3 stars. 2 of them are very similar to our Sun. There's Alpha Centauri A and Alpha Centauri B. Both of them are something that we call Sun-like stars. A is even the same spectral type, has the same surface temperature as the Sun. It's a little bit more massive. It's about 10% more massive than our star. While Alpha Centauri B is about 10% less massive than our Sun. And for both of these stars, we know that they actually contain more heavy chemical elements, so the metals that we astronomers call everything on the periodic table, beyond hydrogen and helium, about 50% more than our Sun. And that's very interesting when it comes to a planet formation perspective, because one of the very earliest results that came out of these exoplanet surveys was that our detection efficiency goes up, so the occurrence rates for at least giant planets around stars with higher metallicity than the Sun, the occurrence rates are higher. So this already makes Alpha Centauri a very attractive target. But A and B are not alone. There's Alpha Centauri C, Proxima Centauri, spectral class M5, main sequence M55. It's about 12% the Sun's mass. It's almost at the bottom end of the main sequence. It's almost, where hydrogen burning is no longer possible. It has about 120 times the mass of Jupiter, and is just slightly bigger than Jupiter itself. That's the nearest star to us, but we can't see it, of course, with our naked eyes. It's visual magnitude 11, way too faint to be seen. But what makes also from an exoplanet perspective, as well as from the public perspective, Alpha Centauri so special, is of course its proximity. So it's 1.34 parsecs, just a little bit over 4 light years away from us, or 230,000 astronomical units. So that's very close, of course, for galactic distances. So when Cameron and collaborators published in 2009, released the movie Avatar, this was one special case when Alpha Centauri rose to public awareness. It's a special system. And of course, it's so special because of its proximity. So they showed a spaceship that made it to that system. They never tell you how fast it goes, but with these distances, of course, you just need 10% of the speed of light to be there maybe in 50 years. So it makes kind of sense. It's reasonable to argue that probably the very first star system that humans will ever travel to, or not with a crew, but with a robotic space probe, of course, will be Alpha Centauri. And James Cameron envisioned a habitable world around Alpha Centauri A called Pandora. And interestingly, this is a funny thing for me, it was not an Earth-like planet in the typical habitable zone of its star, so where the distance is just right, that on a rocky planet you could have liquid surface water. No, he wanted to show something a little bit more exotic. So Pandora itself is a moon. It's a large moon around a gas giant in the background called Polyphemus. And the funny thing for me was that part of my PhD work was to calculate upper mass limits for planets that are possible in the Alpha Centauri system. And I published many years earlier a limit that showed that this planet is not there, cannot be there. We would have already seen it. One thing that sometimes gets forgotten is a very important thing for Alpha Centauri. Alpha Centauri is a binary system. A and B are in a binary orbit. They represent a dual star binary. Whether our Proxima Centauri is actually also part of that system is not clear. It might be just a common proper motion star, or it might be actually gravitationally bound to the inner binary AB. But it's at a very large distance, about 15,000 AU away. So for the remainder of the talk, despite that I was also looking for planets around Proxima Centauri, I will only limit myself to Alpha Centauri A and B. So this is the situation. You have an 80-year orbital period, a semi-major axis, so a typical average distance of 23 astronomical units. So this is solar system distances. It's not a circular orbit. It's 0.5. It's quite eccentric. And the inclination to the sky, to the plane of the sky, is 80 degrees. Unfortunately, not 90 degrees, because then we could argue, well, any planet that exists in the system is maybe more likely to be coplanar to the binary orbit, and then the transit probability would be quite high. But they're not. They're just nearly 90 degrees. So this is the situation. This is the diagram now focused on or centered on A. And this is the apparent trajectory or orbit of B, while this is the true orbit of B. And we are right now here. And you see immediately one thing comes apparent, and this is a very important thing for planet searches. These two stars can get pretty close together, projected on the sky. It turns out right here, they're just 2 arcseconds apart. So what that means in terms of planet formation, when first people started to look for planets, wasn't really clear. We still have not a very concise picture of planet formation. In particular, the Kepler results from the spectacular success of NASA's Kepler mission showed that planet formation is different than what we previously thought. We kind of had just the solar system as a good example, and then we had, for instance, the hot Jupiters that told us that planetary migration, early planetary migration, have to occur too. So we have to have two different scenarios, and planet formation has to be working for both of these scenarios. But the true, real, middle average planet formation process around a typical star in the galaxy is actually still eluding us. And maybe we have been focusing too much on these two extrema, our solar system and the hot Jupiters, while many of the Kepler systems, most of the Kepler systems, I should say, look completely different. They're not solar systems and they're not hot Jupiters. So we don't know really what's going on in terms of planet formation in the Alpha Centauri system. How would we look for planets in this system? Well, we would use a technique that has been proven for a very, very long time, the radio velocity technique. And we would search each individual star. And because it's a binary, we know that around both of these stars, there is only a certain region that planetary orbits can be stable. And they're relatively close to each star. So there can't be a Jupiter at 5 astronomical units that would be right in between the two stars at one point, when they get as close as about 11 astronomical units. So that's just dynamically ruled out. When it comes to the radio velocity technique, it's more sensitive to planets in close-in orbits. And there's our friend Proxima, very far away. And Proxima is too low mass to actually change any types of planet formation processes or the dynamics in this system too much. When it comes to planets, it's still an incredibly interesting question whether Proxima is gravitationally bound to AB, because if that's the case, it has an orbital period of about 1 million years, and that could mean that, for instance, cometary orbits could be perturbed by Proxima, which could help possibly with water delivery to any potential planets that form either around B or A. And this green area here is the classic habitable zone, meaning surface liquid water. So this is the technique that we have been using for a very, very long time. And the transit technique, the alternative to it, is, together with the radio velocity technique, the most efficient way to find planets. And if you target one star in particular, like we did with Alpha Centauri, then you want to do this, because the transit probability for one particular star is always relatively low. And as you saw in the movie, what we do, of course, is we monitor the shift of spectral lines back and forth as the star has to orbit the common center of mass with its companion. So this was the first technique used to search for any kind of companions that we didn't know about around Alpha Cent A and B. And we got to a radio velocity precision of around 50 to 100, I should say, sometimes to about 50 meters a second in terms of the precision, how to measure the stellar velocity along the line of sight. Was in the late 80s in that order of around maybe 50 meters a second. And Colleen Murdoch and John Hernshaw and collaborators published in 1993, at least to my knowledge, the first radio velocity limits for Alpha Centauri A and B. And these dots here represent the area where they basically claim to have, they would have detected every companion. So you have period versus mass of the secondary in Jupiter masses, while the solid lines are actually astrometric mass limits. Because Alpha Centauri is so close, we get very good parallax and astrometry, so a massive Jupiter-type companion would have been even visible at that point of time already as a perturbing orbit in the astrometric solution. So the astrometric limits were quite good at larger separation, while the radio velocity did a better job in the inner parts of the system. So here 10, here 5 Jupiter masses. And then I entered into this whole game by doing my PhD for the one of the first high-precision radio velocity surveys in the southern hemisphere. We used a small telescope at Isola Sia, a 1.4-meter telescope, with a high-resolution spectrograph. We got to a precision of around 12 meters a second for both components. So what you see here are the data plotted versus time. And this huge variation in both stars is, of course, the binary orbit. That's the biggest signal that you have in radio velocity for these two stars. But once you see, it's not over many years, of course, a very very easy to subtract trend, and here the residuals. And there's no obvious modulation going on. So I used these data then in about 2001 to calculate which planets I can already rule out around both of these stars. And I got these limits. Here's separation in AU, masses in Jupiter masses. And around here would be, if that gas giant of James Cameron had 1 Jupiter mass, would be the planet that I would have definitely already seen in these data. So gas giants are unlikely to exist in this system. In particular, if you combine our results with the results from dynamics. It's relatively straightforward to calculate at which distances orbits become unstable due to the perturbations of the other star. And it's for both stars, interestingly, around 3 AU. So here, you wouldn't have any planets anymore. So the only possibility would be these regions in the Alpha Centauri system. That's about giant planets. But what about small planets? What about terrestrial mass planets, Earth-like planets? And people, of course, try to figure this out. If the observational data is not there yet, let's come from the side from theoretical modeling. So this is from a paper from 2008, Guedes and Greg Laughlin and collaborators. They formed planets. First, they laid a planetesimal disk out around each star, and then let time evolve and let accretion occur, and see how this accretion process is working. And this is for Alpha Centauri B. And they gave a very optimistic result. They said nearly 40%, slightly more than 40% of the simulations actually resulted in an Earth mass planet. Here's the comparison to the solar system in the habitable zone of Alpha Centauri B. They were in particular interested in Alpha Centauri B because it's the more attractive target when it comes to radio velocity surveys. It's a cooler star, so you have more absorption lines in the spectrum. That helps a little, but it's also a little quieter star in terms of its magnetic activity, and radio velocity measurements are impacted by stellar activity. So if you could choose between the two stars, you would go for B. But then came another paper, and actually another paper after that showed, no, this is too simple. You have to include a more sophisticated and dynamical study by looking very carefully at the gravitational perturbations caused by the other star on the disk. And Febol et al., they concluded it would never get to that stage of these large planets because due to these perturbations from the other stars, those planetesimals would, their velocities would exceed the velocities of constructive accretion. So they would grind themselves because the impacts will always be at much higher velocities. They would grind themselves down to dust. So we are now in the, and then there was another paper that said, no, not so fast. You have to include gas drag too, and it's maybe possible still. So as an observer, we were in the perfect position now to say, hang on. We have contradicting theoretical predictions. So this is the perfect time now to do an experiment, to do the actual observations again. But they are, of course, very challenging. Why are they very challenging? Well, so far I've shown you, for now, today's standards, relative low precision radio velocities, of the order of maybe 10 meters a second, while today's state-of-the-art instrument delivers about a meter a second in terms of precision, or slightly better even. And what we are looking for is the radial velocity amplitude k of a signal that's depending on the period, eccentricity, mass of the star, and the planet. So for our solar system, this means that the sun, if, for instance, Alpha Centauri astronomers would look at the sun, they would see a radial velocity variation from Jupiter, caused by Jupiter over a period of 12 years, of k equals 12.45 meters a second. So plus minus 12.5 meters a second. But the Earth is so low mass that the amplitude would be 9 centimeters a second. So while this is possible with the instruments and data analysis procedures that we have been using until then, the 9 centimeters a second are way off. And for the Alpha Centauri system in particular, here's Alpha Centauri A, here's B, here's the distance in AU. These are the signal amplitudes for planets of 1 Earth mass and 10 Earth mass and at these periods. And habitable zone distances would be in this range here. So we're talking at 0.6 astronomical units of a little bit over 10 centimeters a second. So this is an order of magnitude below even the current best instrumental precision. So what do you do? Even if you can show this is now the best time to start an experiment, but we don't have a spectrometer or any analysis technique that can give you 10 centimeters a second or better radial velocity precision. Well, you do this. This has been overlooked in our community for a very long time, but it's a very, very old known signal detection problem. It's pretty straightforward. If your errors are not dominated by systematics and are mostly uncorrelated, it's really just a matter of taking enough data. You can find relatively easily signals that are way below your individual measurement precision. And the plot I show here is from an old paper from Bill Cochran and Artie Hatzis, 1996. And these F values mean basically levels of significance. They're called false alarm probabilities. So the solid line is the highest significance that a signal is detected. And on this axis, you see basically the how much bigger the amplitude of the signal is when it comes compared to the noise, so the measurement precision. And right around here, when you take a horizontal cut, you see that with enough data, you can get a signal that's of the same amplitude as your measurement uncertainties, quite easily confirmed. But we are talking about a signal that's an order of magnitude or more, not several orders of magnitude, but maybe a factor 30 to below your measurement precision. So you need to take a lot of data, and I think, as far as I know, Greg Laughlin at UC Santa Cruz was the first one who said, well, but now would be the time to basically dedicate a planet search program onto just 1 or maybe 2 stars and take a ridiculous amount of data, something like 10 to the 5th. And then you would very easily and clearly detect a signal of 10 centimeters a second at a period of maybe 1 year. And that was a very, very interesting suggestion. And I really also wanted to return to my old friend, Alpha Centauri. And when I talked to Stuart Barnes, who got his PhD from the University of Canterbury in Christchurch, he told me about the spectrograph where they were not so, they struggled a little bit to obtain high precision radio velocities, one of the things that this instrument was designed for and was built for. So I told him, well, I was familiar more with a different approach. So there are two ways that you can do to go to a very high radio velocity precision with your spectrograph. You can either stabilize it, basically mechanically, and the illumination of the spectrograph, or you can somehow superimpose simultaneous with the starlight reference spectrum, and that's what we do at Texas. That's what I did for my PhD thesis, so I was very familiar with this method. I said, well, let's combine those two. Why don't we do this? So as many, I'm pretty sure many astronomical projects started, we had this conversation in a pub, and we determined we should do this using an instrument at Mount John University Observatory, which is in the middle of the South Island of beautiful New Zealand. You have the Southern Alps here in the background. And one of the major items why we decided to go there was the position of Alpha Centauri in the sky. It's at -60 declination. So if you have an observatory which is at 44 degrees southern latitude, Alpha Centauri becomes circumpolar, or is circumpolar. So here it is shown, this is Alpha Centauri at its lower culmination at this observatory. We were not alone. There were other groups who decided to do this. One is the group, the Geneva group, around Michel Mayor, using the ISO 3.6 and HARPS. HARPS is that spectrograph which delivers currently the best radio velocity precision of a meter a second or better. And Deborah Fisher at Yale started a program at CTIO. So these two observatories are in Chile. They're roughly at 30 degrees southern latitude. So they cannot observe Alpha Centauri all year long. So we thought we had a competitive edge over them, because if you're looking for a period of 1 year, roughly, then it's really good that you don't have gaps in your data with a periodicity of 1 year. Let me introduce the team. So this is Stuart Barnes, who I had this talk at the pub to start this whole project. And then I want to mention Pam Kilmartin, Eric Brock, and Fraser Gunn. These are real heroes, because we decided to start an observing campaign of these two stars, where we collected thousands and thousands of spectra. So these were the observers who sat there for many, many nights, just taking hundreds and thousands of spectra. Not 100,000, but hundreds and hundreds and thousands of spectra of Alpha Centauri A and B. Another person I want to mention is Christoph Bergmann, who was becoming very important with this project, because he basically adopted it as his PhD thesis, and he was the one who really worked on most of the results that I will show you in a minute. And the whole project was funded by the Marsden Society of the Royal Academy of Science of New Zealand, with Professor John Hernshaw as PI. So we used this telescope, the 1 meter McLellan telescope, here's the dome, and in combination with a high-resolution spectrograph called Hercules. And my contribution was then at the very beginning immediately to provide an iodine cell. What's an iodine cell? Well, that's a little glass tube filled with molecular iodine vapor that you let the starlight pass through. So despite that the instrument is in a vacuum tank and stabilized to some degree, it's not stabilized to such a degree like HARPS, for instance. So we were hopeful we would get a very high radio velocity precision by combining these two techniques. And what you do in this iodine cell technique is, since the starlight passes through the iodine cell has a very complex molecular absorption spectrum. So there are thousands and thousands of sharp absorption lines that get superimposed while you observe the star on the spectrum. And they're rich on all types of information. In particular, information about the spectrograph itself, in terms of how it feels while it's taking the spectrum. You can model these data. You subdivide them typically into small chunks only of maybe 100 to 200 pixel. And you use a measured laboratory spectrum of the iodine that you convolve with model instrumental profiles or point spread functions to match the observations. And you see that they are varying. And that's exactly what the iodine cell took out. If you don't have the iodine cell, any varying PSF would give you fake Doppler shifts of the spectrum. So these are the first data that we got at the beginning. It 2 runs and more, and again, this is Alpha Centauri A. Again, the large trend is due to the binary orbit. Subtracting it, we got immediately under 3 meters a second. We were very happy with these data, and that was also why we probably got funded soon after this. But then time progressed, and our radial velocity data looked like this, with deviations of, look at the scale, it's hundreds of meters a second. So these data look now like the dog played with it. And we actually expected this to occur, because there's something that happens with Alpha Centauri, or happened over the past few years, that's just unavoidable. They got too close in the sky. So in this binary orbit, we were unfortunately starting this just at the wrong moment in time. When the projected binary orbit in the sky means that these stars are still, right now, still approaching each other. And here's a real image of the 2 stars. They're, at the time of 2014, were about 4.5 arc seconds apart, while Hercules itself has a 4.5 arc second fiber on sky. So very easily, light from the seeing disk of the other star entered the fiber during our observations. And one of the assumptions for this iodine cell modeling is that we have only one star, and we model only one stellar template and look at its Doppler shifts. So that produced these strong fake shifts of even up to 200 meters a second suddenly. And the situation just got worse, of course, but we thought we can have first maybe a hardware solution to it by installing a pinhole that reduces the diameter of the fiber to 3 arc seconds. Turns out it didn't work either. There's the typical seeing at Mount John, you still get light from the other star into the fiber. I have to want to mention this affects the other 2 precise radial velocity groups too. So HARPS and at CTIO, despite that they have much better natural seeing, by now the stars are so close together that they have to worry about this, and they struggle with this as well. So what was the idea? Well, I had the suggestion to basically expand my old code that I wrote for my PhD and just expand it and add another stellar spectrum to it. So in the whole equation, this is the data. We have 2 Fs, which are the models of the stars, so now we have star A and star B, while the other star will always be a very low signal-to-noise spectrum that entered the fiber as well. And we combine those 2 and model the data with this combined 2 stars. And we have an epsilon parameter in there, which is basically our measurement for the amount of contamination, which varied quite a bit. So our first try was, of course, to do this straightforward like this, and then basically look at the epsilon and see how much the contamination was. That was too unconstrained. So then Christoph in particular, developed techniques to estimate the amount of contamination by looking very carefully at line profiles and feed this as input to the data modeling. And while we were working on this, in 2012 came the big announcement, a huge press release by ESO that the HARPS team has found a planet in the Alpha Centauri system. Using HARPS data over 4 years, much less data than we had already collected at that time, about 450 data points. But HARPS has this very high precision of maybe even 80 centimeters a second. And these were data that were taken right before the two stars were getting too close even for HARPS to be observed. So they had 4 years of data, which started to be more and more higher cadence as the time went by. And the first thing that they saw was that even though they looked at B, the quieter star that I told you, the most dominant signal was the stellar rotation period coming from spot modulation, from cool star spots in the surface. So they actually had to filter this out. And after they filtered the stellar activity signal out, they had a significant residual signal at a 3.24 day orbit and with an amplitude of about 0.5 meters a second, which almost exactly hit the spot of a 1 Earth mass planet. So very important discovery, something that at that time we were almost expecting because of the Kepler results, which showed that 60% of all solar-type stars have small planets close in, and this just fits in there. So it was a very good result, but then it didn't take much, not very long time. Adi Hatzes was publishing a paper. He took the very same data from HARPS that the Geneva group had taken. And he looked at it in a different way, and he used a different analysis method to look for the planets. And he found that there was one particular chunk in these HARPS data where this signal of 3.24 days was very significant, while it almost was not present in other parts of the data. So once he removed that chunk of the data, the signal became much weaker and nearly insignificant. And that's something that's one of the nice things about planetary signals. Unless there are very strong dynamical interactions, a planetary signal stays constant, of course, in amplitude and phase and period. So it shouldn't just be present in some parts of your data and in others it doesn't. So, well, let's say it didn't support the evidence, it actually found support that made a lot of people, including me, quite skeptical. So while Christoph then went on to work on our 2-star contamination radio velocity code, I was interested to now, since we were getting towards the end of the project, to find out, hey, how much can we say about this planet candidate with our data? And we didn't have the final radio velocity results yet. We actually don't have them even now. But I knew, of course, when we had observed those 2 stars. We had about 22,000 data points on Alpha Centauri A and nearly 17,000 data points on Alpha Centauri B. And I took those timestamps and then simulated with various different noise levels of 2, 3, 4, and 5 meters a second, whether I could pull out a planet like the Geneva group had announced. And these different panels all show you the same. It's a so-called power spectrum. So it's telling you whether you find a statistical significant periodicity in the data. So a huge peak like this with a large power means this signal at that period, which is 3.24 days, is highly significant. And the more it drops into this forest of noise, the lower you have its significance. So I injected actually the planet from the Geneva paper and added then my noise and did the same type of analysis, including the stellar activity filtering as the Geneva group, and looked then at the end whether I see it. So if we at the very end, after correcting for the contamination, we would have an error of about a residual uncertainty of 2 meters a second. It's an incredibly significant signal. Of course, because we have 17,000 data points, we have 600 cycles or what of this planet orbit in our data. It's easy. And even with 5 meters a second, conservatively 5 meters a second, we should still see a pretty strong peak at that period. So this was the 3.24 day planet, but what about planets in the habitable zone? They're much more difficult to find because the radial velocity amplitude is also a function of period. It unfortunately decreases with period. So here I simulated a free Earth mass planet at 250 days, and even expected something like a Harp's type of precision in our data. And then we would see it, even maybe at 2 meters a second, we would still think this is a reliable detection. But at 3 or 4, the peak would already sink into the noise. So with this kind of simulations, I was basically just telling myself, what can we expect at the end? What should we be able to see, depending on how the final uncertainties will be? So in all this time, Christoph kept working on this 2-star template version of the radial velocity code. So these were the data that I was showing you earlier. And when Christoph was done with the code, they looked like this. So we were able to reduce something that had 70 meters a second and this large deviation to something very nice of about 3 meters a second, comparable to the data that we had taken very early on in 2009 and 2010 when the stars were not contaminating each other. However, it doesn't look so beautiful looking at all the data. So when you combine all the survey results, they're shown here versus time. The black are the original radial velocities that I calculated using my standard radial velocity code. So they're the contaminated radial velocities. And the green are Christoph's 2-template version. So we see that we still have systematics, particularly here in Alpha Centauri A. We have strong offsets sometimes, depending on the contamination, but it's not that easy, otherwise we could have corrected for that, between individual runs. So these systematics that are still in the data limit us currently to shorter periods. We cannot really say anything with these kind of data for about planets with a period of 1 year. But we are still working on it. What I show you here is not published yet. It's work in progress. What's encouraging is if you look at individual runs and nights within these runs, the data behaves beautifully. So what we really need to do is we have to find the proper correction for the run-to-run offsets. So in the best nights, we got even RMS down below 2 meters a second. And then what we did, what Christoph did, was he said, okay, if I now want to answer the question whether we see that 3.24 day planet in our data, then I can actually do a very similar thing that Artie Hatzis did in his paper. I take these chunks of data and analyze them separately. So he took those run-to-run offsets away empirically, which means we cannot say anything about longer periods, but for periods of about a week and shorter, which is a typical run duration, we can say something. And this is the power spectrum, the periodogram of these data. And at 3.24 days, we are down here, somewhere way down in the noise. And when we saw this, we thought, yeah, well, it's probably expected that we don't see this signal. But should we have seen it? We could test this, of course, by injecting it. And whoop, yes, of course. Injecting that signal of that planet in our data would have shown it very, very clearly. So we cannot confirm this 3.24-day planet either. So let me end and wrap up with the conclusions. We have probably carried out the most intensive observing campaign of the Alpha Centauri system. We did it from a place where you can look at the stars at all year long. And we collected over 20,000 spectra for A, 17,000 spectra for B. We found that the spectral cross-contamination for radio velocity measurements is really a big issue now. And everybody has to deal with this. So that's an interesting question, whether this is really the technique that we should use to look for planets in this system. Our corrected short-term data do not confirm this planet. And there's just a paper that came out 2 weeks ago. It was announced that they also looked at exactly these HARPS data that de Musk et al. In 2012 used for the announcement. And they also concluded that the planet is not real. It's actually just a window function peak. So a window function peak introduced by the sampling of your data. And so the bottom line really of today is there are no confirmed planets found yet in the Alpha Centauri system. I stress yet because I do expect that they're there. Thank you very much.